Friedel's Crafts alkylation is another example of electrophilic aromatic substitution. In this alkylation reaction, we're going to use an alkyl halide as the electrophile. And so the point on the alkyl halide that's connected to the halogen is the carbon that's going to be connected to the benzene ring. Now the alkyl halide, this carbon is a little bit electrophilic, but not nearly enough to react with benzene. So we're going to use a familiar catalyst. We're going to use aluminum chloride as the Lewis acid catalyst. Now this activates the alkyl halide very similarly to what we saw with Br2 and Cl2. So we have a Lewis acid base reaction where this acts as an electron pair acceptor or Lewis acid. This acts as an electron pair donor or Lewis base. We end up forming this complex, which is just like we saw with Br2 and Cl2. Instead of this being a bromine atom or chlorine atom, it's an alkyl group. We then have essentially the loss of a leaving group, which produces this carbocation that's going to ultimately act as our electrophile. Alright, so now we jump into the mechanism, and again, this should look pretty similar to the other EAS mechanisms that we've seen. One of the pi bonds from the benzene undergoes a nucleophilic attack on our electrophile. This time it attacks the carbocation. We form a sigma complex. Again, if you're asked to draw this mechanism, be sure you show the 3 resonance structures that stabilizes the sigma complex. And then we end off with a proton transfer, and this looks exactly like the proton transfer that we saw in the halogenation example. Now, as you can imagine, with the carbocation intermediate, there are going to be some limitations placed on what we can use as the alkyl halide. It turns out we can use ethyl chloride as the electrophile. And that may be surprising because forming this primary carbocation wouldn't seem favorable, and it's not. Since primary carbocations are very unstable, we don't have that step with the loss of a leaving group to actually create the carbocation, and instead this whole complex probably acts together as the electrophile in the case of using ethyl chloride as our alkyl halide. Now, while it works with ethyl chloride, most other primary alkyl halides won't work. When we go to form this complex, we're going to end up getting a hydride shift, creating a secondary carbocation. We know that when carbocations can rearrange, they will. The reason it won't with ethyl chloride is because we just end up with another primary carbocation, so rearrangement doesn't get us anything. But for pretty much all other primary alkyl halides, we'll get this rearrangement to form a secondary or tertiary or whatever the more stable carbocation is, and then we'll end up getting a mixture of products. So generally, other than the ethyl chloride example we saw on the last slide, primary alkyl halides are not used in Friedel's Crafts alkylation, and instead we need to stick with preferably tertiary or secondary alkyl halides. So just to discuss a couple other limitations with this Friedel's Crafts alkylation, we can't use vinyl alkyl halides or aryl alkyl halides in the reaction. Neither of these will react because putting a carbocation directly on an sp2 hybridized carbon is very unstable, and so these won't occur. Another thing that we'll see is that polyalkylation often results. It turns out adding an alkyl group to our benzene ring makes it more susceptible to future attacks, and so we can often add multiple alkyl groups. Now, we can adjust the conditions of the reaction to limit ourselves to mostly monoalkylation, and unless we specify otherwise, we'll assume that we've limited ourselves to those conditions. So we can just focus on the monoalkylation. All right, and then depending on how the benzene ring is substituted, these substituents can actually deactivate the benzene towards wanting to react. And actually, much of the focus of the rest of the chapter is going to be related to these last 2 limitations. How do substituents on the ring influence the electrophilic aromatic substitution? And so we'll get into that much more going forward.